All right, let's get right into it. We've all heard the promise of a 100% renewable energy grid, right? But behind that amazing goal is a huge engineering puzzle. Today, we're going to dig into the hidden physics that keeps our lights on and the absolutely brilliant software that's making that clean energy future a reality. You know, it's a question we almost never think about. We just flip a switch and boom, the power's there. But the answer is this incredibly delicate, high-speed balancing act. And the rules for that balancing act, they're being totally rewritten as we shift away from old fossil fuels and into renewables. So, to really understand where we're going, we first have to look back at the grid we've been using for, well, over 100 years. Its biggest strength came from something surprisingly old school: sheer physical weight. Okay, so here's the crucial idea. Traditional power plants, they have these enormous spinning turbines that weigh hundreds of tons. All that momentum, that physical inertia, it acts like a giant shock absorber for the whole grid. Now, solar panels and wind turbines, they don't have that. They connect to the grid through these quiet, static boxes called inverters. So as we add more and more renewables, we're basically making the grid lighter and lighter, making its rhythm much, much easier to knock off balance. And that is the core problem we're facing. Think about it. A lightning strike, a tree falling on a power line, that's a sudden, violent shock to the system. Without that massive spinning inertia to just power through the disturbance, the grid's frequency can crash in milliseconds, and that could lead to widespread blackouts. So the big question for engineers is, how in the world do you build a stable grid without the flywheel? So if losing all that physical weight is the problem, what's the solution? Well, it turns out if inverters don't have any natural inertia, we can actually teach them to create it artificially. And this is where the electronics get really, really smart. For decades, this grid-following approach worked just fine. I mean, as long as the grid was dominated by those big, spinning generators setting a steady beat, the inverters from solar and wind farms just had to be good little followers. They'd listen for that constant 60 hertz hum and just inject their power in perfect time. It was simple, it was effective, but it was totally passive. And this is the game changer. A grid-forming inverter doesn't just listen for the beat, it can create the beat. It uses these incredibly fast microprocessors and really sophisticated algorithms to act like a massive spinning generator. It can sense a disturbance on the grid and, within milliseconds, use its software to push back, stabilizing everything. It literally creates virtual inertia out of nothing but pure code. But you know, creating this virtual inertia introduces a whole new, fascinating challenge. It's not enough to just pretend you're a heavy flywheel. You also have to be able to keep your balance when you get hit with a big shock. Engineers have a name for this: transient stability. So what does that quote actually mean? Well, the VSC, the voltage source converter, that's the heart of the inverter. And what this is saying is that even these super smart inverters can get knocked off balance. Think of the grid like a tightrope. The virtual inertia helps you stay on the rope, but something called damping is like your balancing pole. It's what helps you absorb a sudden gust of wind and settle back down. Without good damping, you can just start wobbling completely out of control. Right, this is the moment of truth. A fault happens somewhere on the grid, and the voltage suddenly sags. That's the huge gust of wind hitting our tightrope walker. And the critical question becomes, can the inverter's control system handle that shock? Can it dampen out the wobbles and get its balance back? Or is it going to lose sync and fall right off the rope? Now, this is pretty cool. This is how engineers actually visualize that balancing act. It's called a phase portrait. Just think of that center dot D as the tightrope itself, perfectly stable. When a fault hits, the system gets shoved away from that point. In a stable system, like the one this blue line is tracing, it wobbles a bit, but see how it quickly spirals right back to the center? It finds its balance again.
Phew.
But this is what happens when you have poor damping. The system gets the exact same push, but instead of spiraling back in, it just flies completely off the chart. The tightrope walker wobbles more and more and more, and eventually, they fall. The inverter loses synchronization with the grid, and that is a huge risk for causing a blackout. Okay, so if the key is this damping, how do you give our electronic tightrope walker a better balancing pole? Well, it all comes down to the art of tuning the control software. It's this incredibly delicate dance. Engineers can adjust the virtual inertia, but there's a trade-off. If you add too much, it can actually make it harder to recover from a big shock. They can tune things called droop gains, which basically tell the inverter how strongly to react to changes. They can even add electronic filters to kind of smooth out the response, giving it a split second more to react graciously. It's a multivariable balancing act, all happening in microseconds, and it's all defined by code. And here is the proof, right here, straight from the lab. These two graphs show the exact same inverter going through the exact same grid fault. On the left, with bad software tuning, you see those wobbles grow totally wild until the system just falls apart. But on the right, with properly tuned damping, the inverter barely flinches. It rides right through the fault, the wobbles die down almost instantly, and the grid stays stable. The hardware is identical. The only difference is the software. This technology is so fundamental, so absolutely crucial for the future grid, that the researchers and engineers developing it aren't locking it away. No, they're building it out in the open for everyone to see. And this is the group making it happen, the UNIFI Consortium. It's a team of top national labs, universities, and industry experts, all working together. Their goal is to create a common blueprint, a universal set of rules and open standards so that grid-forming inverters from any company can all work together seamlessly. Because at the end of the day, for the grid to work, everyone's equipment has to speak the same language of stability. And they're not just writing academic papers, they are sharing the actual designs. They have created a complete open source reference design that anyone can get their hands on. A university researcher, a startup, anybody. They can go online, download the hardware files, download the control code, build their own grid-forming inverter, and then test it, improve it, and contribute their findings back to the whole community. It's collaborative engineering on a global scale, and it's amazing. Which brings us to our final thought. The old grid, it relied on the brute force of physical inertia. The new grid is going to rely on intelligence, on speed, and on collaboration. By replacing massive chunks of spinning metal with elegant, open source code, the answer to whether we can build a more resilient, 100% renewable grid is looking more and more like a resounding yes.